If a machine is designed to look like us, move like us, and eventually work right alongside us, why does it still tire out so much faster than a human being? Welcome to this explainer. Building a humanoid robot is, without a doubt, the single most demanding energy challenge humanity has ever attempted. Today, we're doing a macro to micro teardown of their physical anatomy. Because look, we aren't just talking about designing a bigger laptop battery here. We are talking about building a highly dynamic, mobile power plant, one that has to survive millisecond-level AI reasoning, constant thermal stress, and high-impact jumps, all within a frame that literally cannot weigh more than a typical human adult.
Here's our roadmap for today. We're going to cover the endurance challenge, the battery bottleneck, power distribution architecture, energy budgets and thermal management, and finally, the solid-state future.
All right, let's dive right into Section 1, the endurance challenge, and why these robots are basically mobile power plants. Think about what we're actually asking these systems to do. We want them to process data at lightning speed, balance on two legs, react instantly to their environment, and carry heavy payloads. It's a massive, massive drain on onboard resources. And to really understand where this is heading, just consider this staggering number, 74 gigawatt hours. By the year 2035, that is the expected demand for high-performance batteries driven solely by the humanoid robot industry. Now, to put that 74 gigawatt hours into perspective, that represents a massive 1,000-fold increase from where we stand today in 2026. 1,000 times. This really shows the sheer scale of the upcoming energy demand. Humanoids aren't just a software challenge, They are about to become one of the largest physical energy storage challenges on the entire planet. And comparing current runtimes reveals our immediate commercial bottleneck. Right now, the typical dynamic runtime hovers right around 2 to 4 hours. For example, Tesla's Optimus Gen 2 utilizes a 2.3 kilowatt-hour battery, but it only manages about 2 hours of intense dynamic work. Agility's Digit stretches across an 8-hour shift, but that's via battery swaps, while Apptronic's Apollo runs for about 4 hours per pack. So we are nowhere near a charge once and work all day paradigm yet. Which brings us to Section 2, the battery bottlenecks, and how we're hitting the density wall. Okay, so the gold standard for humanoids right now involves the same 27700 NMC or NCMA high nickel cells you'd find in electric vehicles. These are supplied by heavy hitters like Samsung SDI and LG Energy Solution. But here's the problem. We are hitting the physical limits of liquid lithium-ion density, which maxes out at roughly 200 watt-hours per kilogram. And it's a catch-22. If you add more batteries to a robot, you add more weight. And if you add more weight, well, the motors have to work harder to move the robot, which immediately drains the extra battery capacity you just added. It's a vicious, inescapable cycle of physics. So how exactly is the industry bypassing this density wall? Well, there are 3 main paths right now. First up is autonomous hot swapping. Companies like Agility and Apptronic use modular packs, while Boston Dynamics' Electric Atlas actually navigates to a station for an autonomous 3-minute belly swap. Pretty wild, right? Second is wireless inductive charging. The Figure 03 robot uses a 2-kilowatt wireless footpad, meaning it just stands in a designated spot to fuel up. And the third path? The push for next-generation solid-state batteries. Chinese firms like XPeng are already testing solid-state prototypes to support heavy onboard AI tasks that would normally drain a standard battery in minutes. Let's move to Section 3, power distribution architecture, which is essentially the robot's nervous system. I want to pose a question to you. Why has the entire humanoid robotics industry virtually converged on a 48-volt to 52-volt DC bus to move power? I mean, you don't see 110 volts, and you definitely don't see 12 volts running the main lines. So why exactly 48? Well, it turns out human safety directly dictates the robot's internal engineering. 48 volts stays safely below the 60-volt human interaction safety margin. This means if a wire gets exposed or there's a short, it won't be lethal to a human working right next to it. But it's still high enough to reduce resistive line losses. From that main line, the power splits perfectly. You've got a 48-volt actuator rail powering the heavy motors, a stepped-down 12-volt peripheral rail for cooling fans and smaller LED lighting, and finally, a highly sensitive 1 to 5-volt logic rail. Now, that 1 to 5-volt logic rail might sound incredibly small, but it's what powers the perception stack and the AI brain. An NVIDIA Jetson AGX Orin can draw between 15 and 60 watts all on its own. And because of this massive draw, we're actually seeing a big shift toward FPGA acceleration. Recent research shows that using FPGAs like the Xilinx ZCU-102 can result in a 5.4 times reduction in energy usage for complex control loops compared to standard CPUs. That is a real game changer. And then, of course, you have the sensor debate.
LiDAR gives precise 3D geometry but draws massive power per sensor, whereas vision-only compute lowers mechanical complexity but demands much heavier neural network processing.
Moving into Section 4, budgets and thermal management, or as I like to call it, brute force physics. Let's think about the brutal difference in energy budgets across a single robotic frame. A leg subsystem needs to support the entire weight of the robot and absorb shock that requires a massive 3 kilowatt to 4 kilowatt peak burst of power just to execute a jump. Meanwhile, an arm subsystem might only need 1 to 2 kilowatts during dynamic lifting, so the power system has to be smart enough to dynamically shunt massive spikes of current down to the legs, all without starving the brain or the arms. And at the absolute end of the line, you have the hands. A typical highly dexterous robot hand has 11 degrees of freedom, sometimes even more. Even tiny micro-movements to grip a tool drain power. This is exactly why integrated smart motor packages are so absolutely crucial. Take the 9mm intelligent motors developed by MPS, featuring 14-bit absolute position encoders. By combining the motor, the sensor, and the controller into one tiny package, engineers can eliminate heavy, inefficient external wiring, which saves precious energy. But there is a catch. All this energy movement creates a serious byproduct, and that is heat. When you're dumping thousands of watts into actuators housed inside aesthetic, tightly sealed skins, you generate intense, localized heat. These components literally must be actively cooled with 12-volt DC fans. Why? Because the lithium-ion batteries at the core of the robot will fail or, even worse, experience thermal runaway if they're pushed outside their optimal operating zone of 20 to 45 degrees Celsius. So thermal management is every bit as critical as the motors themselves. Finally, Section 5, the solid-state future and how we are shattering the limits. We're talking about completely replacing standard liquid lithium-ion tech with solid-state. Innovators like QuantumScape, Lighten, and Solid Power are replacing liquid electrolytes with solid materials, which allows them to use a lithium metal anode. And this single change can push energy densities way past 500 watt-hours per kilogram. In the real world, that means you can double or even triple the runtime of a humanoid robot without adding a single ounce of extra weight. So, the crucial takeaway here is exactly what TrendForce notes. The true gatekeeper of humanoid commercialization isn't just the flashy AI software allowing them to fold laundry or move boxes. It's the fundamental physical chemistry of the batteries powering them. Solid-state technology is really the ultimate key that unlocks uninterrupted 24/7 autonomous labor. I'll leave you with this question to think about. When the solid-state revolution finally arrives and robots are no longer tethered by a short 2-hour battery life, what limits will humanoids shatter next? We are standing right on the precipice of a massive shift in physical labor and automated energy systems. Thank you so much for joining me for this explainer. I really hope this gave you a completely new perspective on the invisible energy networks keeping these incredible machines standing. Keep learning, and I'll catch you next time.